All right.
Yes.
Everything's starting. All right. Let's get right into it, okay? We have identified basic facts about principles, capabilities, limitations of satellite and receive system. Satellite transmit and receive. Just remember you got to get 28 out of 40 to pass the test. Good news from yesterday, everybody passed. Good thing. We always have the AFSC application. We're going to be looking at satellite-based equipment. So we're going to look at the basic radio picture as well as fundamental radio parameters, radio performance assessment, and ancillary function. Now, not sure if you have it, or if you do, that's great. This is a blank worksheet for your basic radio to give you an idea how to use transmit and receive for the basic system. Now, if you turn this in, great. I'll look at it and say yay or nay. Or if it's got a few problems, I'll let you know about them. But there is a filled out portion in the lesson for today. Top part is transmit, the bottom part is receive. Now, with the basic radio picture, we look at an objective and how we're going to work things out. Again, this is a very basic radio picture. This is a transmit path. The objective is transmitting baseband, which is the aggregate coming out of the multiplexer, and we're going to send it to the dissonant. How are we going to do it? Well, it's accomplished in 3 steps. You got modulation, up conversion, and amplification. That is its order. So we're going to take necessary steps and first run it through the baseband. Is going to run it through a modulator. We're going to modulate it into a intermediate frequency. And depending on the equipment, it could be anywhere between 70 megahertz all the way up to 30 gigahertz. Again, it depends on the equipment, what it is. So we're going to take it, that IF, and we're going to up convert it. We're going to make sure it goes from IF to RF. Now, we're going to use something called a local oscillator using phase lock loop. And getting that frequency, and it's going to mix with the IF to get it up to the RF. And of course, the last stage with anything, anytime you manipulate the information, you need to amplify it. So we're going to use what's called an HPA, high-powered amplifier, and that's what's going to get it to the dissonant. The next thing is now we're into receive. So the dissonant's got to do, we just sent it to the dissonant. What is the dissonant going to do? Well, it's going to recover the baseband, and that is the receive path. There are 3 steps. You have RF signal recovery, down conversion, and demodulation. It is pretty much the same thing as transmit, except it's in reverse. That's it. So you're doing the same thing, just in reverse. We have RF signal recovery, down conversion, demodulation. Let's take a look at these. So the first one, the thing we're going to go through is something called an LNA, low noise amplifier. Because it's such a weak signal coming into the antenna, we're going to have to do something called amplification. Now, the idea behind this is we're going to amplify it at the same time we're trying to eliminate some of the noise and everything else, so we can pull that signal out for the demodulation process later on down the circuitry. We're now going to hit the down converter, so we're going to take that RF we just amplified and convert it from RF to IF. Again, you're going to need a local oscillator in order to get that signal down. Show you that. And then we're going to go into something called a demodulator. Well, just like the last stage, or the first stage in transmit, we modulate it. Now we're going to demodulate it, which is the last stage in receive. You'll notice that last sentence there, it says AGC circuit is going to provide us a constant output. We'll get into that in just a few. Remember I told you that we have the filled out version? Here it is. Okay. The multiplexer is going to send us an aggregate. It's going to go into the radio itself, and then it's going to modulate it. Now, you guys seen this in block 2 with the PRIC 150 going from analog using your voice and getting it into digital, which is pretty much the representation of an aggregate signal from a multiplexer. It's simplistic, but it's on the same level. So you're going to modulate it onto a carrier. In this case, it's going to be an intermediate frequency, and then we're going to go through an up converter, and then we're going to use a high-powered amplifier to amplify it out and send it to the dissonant. And then in return, we're going to receive it, go through an LNA. There's your amplifier, eliminate some of the noise, get to the down converter, take that RF to IF, and then use a demodulator to get the aggregate out so we can send it to the demultiplexer so it can send it to the different channels. This is the other side of the scenario where we show you the differences. You'll need to kind of understand what the circles with the X's and the little squiggly line in the circles and then the triangle, just to give you an idea. Normally circles with an X is considered a mixer. The little squiggly line or the AC signal in the circle are the oscillators. And then the triangles are your amplifiers. So you can see this is pretty much the basic radio picture, just drawn out a little bit more technical in how we're going to work things. Again, this is a full duplex system. That means that you can transmit while you're receiving on 2 different frequencies at the same time. We also have something that we go through called a branch assembly. The branch assembly is a passive devices in this case where there is no electricity provided, but it does some important parts with it. So let's take a look at this. What does it do? Well, first of all, you got to get the frequencies to and from the antenna. There are some portions of this branch assembly that eliminates harmonics and noise. And of course, it does aid in receiver selectivity because you don't want the whole spectrum coming through. You need to be a little bit more selective. And then, of course, you got something that monitors the output power. So let's go through these. So the first thing we look at is an isolator. It's a circle with an arrow. The easiest way to understand this device is whatever way the arrow is going, that's the flow of the RF. Normally these are RF devices that we're dealing with in the branch circuit. You'll notice that when I said that's the flow of the RF, well, what happens if you get RF that comes back in? Well, that isolator is going to prevent that from coming back. That's the whole idea behind an isolator. Separates one circuitry from the other. A one-way device. Next up, we have something called directional, or what they call dual couplers. Now, you guys have played with this back in block 1. You probably didn't even realize it. Well, it's called a digital wattmeter, and it has 2 elements that you can use with it. One is for forward power, the other one is for reflected power, and they are nothing more than RF diodes. That's their whole intention. So one diode you notice was pointing toward the dummy load. That is your forward power. The other element is pointing away from the dummy load. And this is in block 1 now. Hopefully you remember that device. That is your reflected power. Okay, forward power, good. Reflected power, bad. That's what you don't want, is reflected power. Because reflected power is nothing more than heat dissipated when things aren't going its way. And if the radio's getting really hot, maybe you might want to look at your antenna or your coupler. So we also have something called filters. It can be either tunable filters or just regular straight up crystal filters. I've seen different variations, bandpass filters, but in this case we're going to have what's called a tunable filter. And the idea behind it is we're going to take this full spectrum that's out there and we're going to narrow it down into a small portion of that spectrum because that's the only one I want. And the idea behind it is I'm rejecting all the other frequencies and I'm able to get the noise or mostly out, and it helps us with getting what frequency I need into or out of the equipment. There's also something called circulators. Now, if you look this up in Google, which will be fun, you'll see that it is a device where it'll have, in our case, it'll be a 3-port. They have a 4-port one out there. And the idea behind it is we're going to be routing our RF certain ways. We have a circulator on the tisser right at the front or back end of the radio, depending on if you're in receive or transmit. It is a 3-port circulator. I think it's considered a diplexer in our case. And the object is we need to keep the receive signal separate from the transmit signal because it is a full duplex system and you're using it at the same time, or the antenna at the same time as you're transmitting and receiving. It's not that complex. Again, it's a passive device. There is no power that is able to get to this thing and determine which way it goes. It's all done by the impedance and the circuitry that's in there. Normally it's a it looks like a washer, not the clothes washer, but washers that you put with screws, and it's kind of thick, probably about a 1/2 inch thick, and you got coils that go around it. That's one style of the circulator that I have seen, and when they break it out you also have inductors and a couple other things in there, but is somehow able, because of the impedance, determine which is transmit and which is receive and be able to input and output of that particular device. And I don't know how it keep it separate, but I understand the concepts of impedance with it, because one frequency is going to be one impedance and another frequency is going to be a different impedance, so it's able to determine which way those things are going. This is what a diplexer could look like. I've used these on my satellite dish when I had them. Pretty ingenious. This is straight out of Google using images and the Wikipedia. We also have duplexers. I've used the one on the right hand side. We call them cans, and that is when we have two frequencies really close, and you guys have heard the word mutual interference. Well, normally we use those particular type to help eliminate most of the mutual interference. Still happens out there, but it's really unique how those, what I call the RF cans, can be able to separate out the frequencies. This is what the actual device could look like in a circuitry. Notice this is a 3-port. There are 4 ports out there. Remember I told you about AGC? Well, here it is. We have something called RSL, AGC, volts, gain, and output. RSL means receive signal level. Anytime that I see AGC, I always relate it to receiving the signal. I've not seen AGC in transmit. Now, I've seen ALC, automatic load control. I've seen transmit gain control. And there's a couple others out there that I probably haven't, that I could mention, but you guys can figure it out. Transmit, on the transmit side, they got different names, but when it comes to receive, everybody seems to be on the same page from the manufacturer's standpoint. When they talk about AGC, it's always a receive term. Now let's go through this just to give you an idea. So the backdrop is I've always been in the air traffic control environment when I'm dealing with most of my, or at least when I went through the Air Force, that has been my expertise. And it doesn't mean that I haven't worked on satellites or giant voice or any of that other stuff. It just seems like that has been the area where I've been put in the most. But I do have variations on what I've done out in the past. RSL, receive signal level. That is the receive signal coming in. Now, what has that got to do with air traffic control? Well, when a plane is 200 miles out, and let's just say you didn't have AGC, and they broadcast to you, that signal is going to be extremely weak. So you, the controller, is going to have to get up there and turn that knob all the way up. As the plane gets closer to the base to land, and it starts talking to you more and more, you're going to have to start turning that volume down because the signal's getting stronger. Well, when it lands, you're probably being blasted out, so you got to turn that thing almost all the way down just so you can understand what this individual in the plane is telling you, and vice versa. Well, when a plane leaves, it's pretty loud, so you got the volume turned all the way, pretty close to down or off. As it leaves, it gets farther out, and you got to start turning that volume control up. So what AGC does for us, it takes the human element out of it. So when the plane gets closer, it's going to start reducing the gain until it gets there. And, the idea is to have that constant output. When the plane leaves, that AGC is going to compensate as the plane keeps going further and further out. And that's pretty much what RSL is right now, is that's that receive signal level from the plane either coming in or going out. So let's go look at when it's coming in. So as the plane keeps coming in, the RSL, receive signal level, is going to increase. And of course our AGC is a representation of the receive level. In this case, it's going to be voltage. It's also going to go up. The whole idea behind getting that circuitry correct is bringing the gain down so my output stays at a nice, comfortable listening level. So let's do the reverse. The plane's going out. In our case, as it keeps going further and further out, it's going to have a weaker signal. AGC is going to represent it, but my gain's got to start increasing to keep our output constant. So I'm not constantly varying the volume control button as planes go in and out of the base there. So what can we say about it? Well, RSL and AGC voltage are directly proportional. So if you've been following along in these lines that we've been looking at, you would notice that. So when you look at RSL gain, they're inversely proportional. What's the object behind AGC? Keep the gain constant, so you don't have to keep varying the volume control button. That's what AGC does for us. We're going to look at radio parameters called frequency, accuracy, and stability, bandwidth, frequency response, selectivity, gain, and sensitivity. So the first one, frequency, accuracy, and stability. This one relies solely on the oscillator. If you have a crappy oscillator, you're going to have crappy accuracy and crappy stability. Now, to compensate for some of that, you're going to have something called phase lock loop. The idea here is to keep your frequency on frequency so where it doesn't drift. When looking at this, if you have a good quality oscillator, the phase lock loop doesn't have to work as hard to keep it accurate and stable. So that's the whole idea behind phase lock loop, is to keep it accurate and stable. Crappy oscillator, phase lock loop is going to have to work really hard to keep it accurate and stable. Good oscillator, it's going to have to work less. Next up, we have bandwidth. Now this one can be used different modes. In our case, when we're dealing with radios, we're going to be talking about the frequency range. Let's look at frequency response. Now, has anybody out there purchased a pretty decent stereo system lately? No? Maybe?
Yes, sir.
All right. What did you get?
It wasn't exactly a stereo system, but it was a very expensive pair of headphones I needed an amplifier for.
All right.
It was the Sennheiser
Ooh.
X6XX.
Okay.
So the 650, but a limited version of it.
Okay. I like Sennheiser. I got one myself. It is really nice. So let me ask you, did you ever look at the frequency response on it?
I did not.
Okay. Those are in your specifications. It is, and this is a definition, and the reason why, was trying to find out if anybody did it. If you actually looked at your specification and judged the headphones on your frequency response, you would have found out that really good headphones have a very, very small percentage. That's its tolerance. With less than favorable headphones, and I've purchased a few, the frequency response, the number is higher. And it's like 0.001 for, let's say, a Sennheiser compared to, let's say, an Audio Technique that you just bought off of Walmart. It'll probably have 0.05% for the frequency response. So the lower the number, the better it is. Why? Because you have frequency range over which an audio device, in some cases system, will produce and reproduce a signal within a certain tolerance. So if you get a really good set of headphones with a very low percentage as far as frequency response, it's going to sound just like it was if you were there. Unless you have, the system is, you're only as good as your weakest system. So it's good on you that you bought that Sennheiser. It's a really good product. And thank you for sharing it. Selectivity.
You're welcome, sir.
Yeah. Oh, I appreciate it. I didn't know people knew about Sennheiser. Yeah, everybody thinks Bose and Sony and all those are good. Yeah, but Sennheiser is good. Selectivity.
Yes, sir.
Selectivity is the ability to process desired frequencies and reject undesired frequencies. Remember, you are trying to get a certain area across the frequency spectrum in order to process a certain frequency or frequencies. That's the idea behind selectivity. If you did not have any selectivity, when you hit that front end of your receiver, it's going to be mixing a ton of signals that you don't want, and it can create chaos at the or when you finally get it to the speaker. Next up, we have gain. I like to equate that to your volume control knob or selector switch on just about anything. You have them on your computers. You can adjust the gain of your headphones if you're listening to it on a headphone, or you're listening to it through your speakers, so you might actually have to turn it up a little bit, especially when you guys have the intercom going off. Sensitivity. This one, you guys have come across the signal plus noise to noise ratio in block 3. This is what it's checking. And you're going, okay, I don't remember, but let me give you a little background on it. Signal plus noise to noise ratio checks. What did you have to do? Well, first of all, you got to figure out this is the threshold of what my radio is supposed to receive at. So I'm going to take that signal. I'm going to look at the signal plus the noise. Normally you're putting in a 1 kHz tone at the front end. The receiver's receiving it. You're processing it at the audio level. And the next step is to eliminate the signal. How are you going to do it? Well, normally you have a filter on it to clean out that one signal, normally that 1 kHz tone when you set it up. And all you're going to hear is noise. The threshold of where the signal plus noise is and where the actual noise floor is has to be at least a minimum of a 10 dB drop or it fails. Better than a 10 dB drop, in other words 11, 12, 13, 14, is good. So that's what sensitivity is checking, is how able this receiver is able to pull the signal out of the noise floor and make it legible. Next up is the systems approach. Oh my goodness, how many times have I done that? So what you guys are going to be doing, well actually I'll just go with the NSM as you guys worked on it. Let's just say that you got called out and your equipment is only the NSM. Okay, you check the NSM out and it's perfect. It's fine. Do you get to go home? No, you don't. Especially if it's 0 dark 30. There's still a problem. You got to figure out where the problem is coming from before you can actually say, I'm done for the night. And one of the ways that I like to say it, you guys saw the NSM, but there was 3 cases total. So you probably would have to go through all 3 cases to figure out if it's on the distant end or it's on your end. So it just goes to show you that just because you troubleshot your equipment does not mean it's time to, hey, my equipment's good, call somebody else out. It doesn't work that way. You got to identify, hey, listen, hey, it looks like one of the users has the problem. Okay, you're going to have to call out the computer guys for that one. This one, you know, I'm able to troubleshoot it to their system, so call them out. That's what you got to do. Also, you have to be nice about it too. That's always difficult. But it just goes to show you that you got to look at the whole system. You just can't look at one piece, which might be just your equipment. You got to figure out, hey, is it a transmit problem or is it a receive problem? Is it, you know, local or is it on the distant end? That's what you got to figure out. So you just can't stop at your equipment. You got to troubleshoot a little bit more than that. Sometimes it pays to go out on a job with someone else just to get an idea of how the system works. So again, just because it's your equipment doesn't necessarily mean that your job ends there. You might have to go that extra mile to find out who or where the trouble lies. Next up, we got quality and reliability and speed. Quality, how close the output resembles the input, close to that fidelity, frequency response. Reliability, percentage of time the system is available. And just to give you an idea, back in the first Iraq War, Desert Shield and Desert Storm, when they were flying the planes, normally the expectation is their planes need to be 85% reliable. In other words, that's the percentage that, you know, when a plane comes back, how quickly they can get it up, which relates to speed too. But they went from an 85 to a 92%, even though they were being shot at and everything else. That is unheard of during a war scenario. Normally it's in the low 60s. Goal is 85%. So that's pretty doggone good. The other part of that reliability is you can use whatever network systems, like AT&T's up most of the time. Every now and then when power goes out, we lose it. Yeah, that's not reliable unless I put something on it to make it, like an UPS unit on my router, but I don't want to spend $300 just so I have internet when it does go out. Doesn't make any sense. Even though I got an UPS on my big computer here. It is reliable, but, how often is the system available? About 98, 99% of the time, unless power goes out. Speed, how quickly the system can process data, which is a good thing. And of course, how quickly you can get your comm up. Like in Block 4, you guys are probably setting up antennas. How quickly are you going to be able to set that antenna up, connect a radio to it, and talk to the distant end? By the way, that's what you're going to be doing in Block 10. Or is it Block 11 now? You get the idea. Anyway, we look at switching, auxiliary channel, performance monitors, and fault indicators with ancillary functions. Take a look at each one of them. Switching, used for redundancy. Now, everybody has heard when you got a server, it goes out. Hopefully you got a backup server and it switches without you even noticing. That is a good thing. When you look at your equipment, you always want to have that redundancy if you can. Now, of course, money talks, because if you got two, that means, hey, I got some really good redundancy. When it switches over, then I can work on the other one that broke. But just make sure that both of them don't break. That would be a bad thing. So that's what they talk about when they look at switching. Auxiliary channel. That is something that's built into the Jerk 239 system, and if I'm not mistaken, the TSC 179, which is Block 9 and 10 now, or is it? Yeah. It's a SATCOM gear that you guys walk by. It also has something what we call order wire. Order wire is that auxiliary channel. What does it mean? It means it's our own separate channel, and it doesn't take away from the mission traffic. Pretty cool, huh? So we actually have our own separate channel. So we do have a way to troubleshoot even if the mission traffic is down. That's what makes it so valuable to have our own channel. Because the last thing you want is that mission traffic to go down. But by having that auxiliary channel, we have an avenue to be able to troubleshoot. Remember when we said that systems approach back there? Well, sometimes you might have to get onto the distant end by using that auxiliary channel because you have maybe a user that's down, but not all of the mission traffic. And the last thing you want to do is try to degradate that mission traffic. Next up, we have performance monitors and fault indicators. All right, so what the heck is a performance monitor? Well, it could be a meter, it could be a light, it could be, let's just say, using your test equipment. Those are all performance monitors. It just depends on what the equipment is and what you need it to do. For example, when you're looking at the Jerk 239, it has meter. Actually, it has 2 meters, one on each assembly. Then it has a whole bunch of lights. So if one light is on and the TO is saying that light is supposed to be lit, that's a good thing. If the light is on and the TO says it's not supposed to be on, it might be a bad thing. It also goes and falls in the line of fault indicators. You got visual and audible alarms. This is to aid us in figuring out, hey, have we made a mistake somewhere? And when you guys go into the TISR lab, you're going to find out that there's going to be places where you accidentally skipped a step and you're scratching your head because one of the lights is lighting and you don't know why. Oh, and by the way, they tell you why in the tech order in chapter 4. If the light is lit, there's reasons for it. Are you in loopback? Are you in operate? You know, what is the scenario? Well, when I do troubleshooting back in the day, and I troubleshot a lot of radios, normally I got called out at 2, 3, 4 o'clock in the morning, and I would go to the site, open the door, and never turned on the light. My first thing was to do a visual on all the radios. Why? Well, if all the lights are green and I got one that's red, bingo, there's my visual. Okay, I can see that I've got a problem on that radio. I can identify it. So that's how I troubleshoot, and I went from there. Because most of your troubleshooting is using your senses. Normally it's hearing. Do I hear a bell going off? Do I see, that's the other one, do I see a light that's lighting that's not supposed to? So the whole idea is to troubleshoot quick and get the equipment back up. Hence, remember the speed earlier? There you go. The redundancy, well, maybe I have a spare radio now that I can just go over and patch it in. So those are just some areas where we're looking at as far as performance and fault indicators. Okay, so we've looked at the basic radio picture, fundamental radio parameters, radio performance assessment, and ancillary functions. So, Abul, question for you. What is the transmit objective for your basic radio?
It is to transmit the baseband to the distant end.
Excellent. Alvarez, do you know what the 3 steps are for it?
I don't, sir.
Okay. Do you know, Bakken?
Is it, are you talking about the multiplexing, modulation, and then amplification?
Yeah, but the first one isn't multiplexing. It's actually modulation. We're taking the multiplexer, the aggregate, and we're modulating it to an IF signal. So Garcia, question for you. What is the objective of the receive? I saw you key up your mic, so I know you're doing
something. Oh, you didn't
something.
hear anything I said? Okay.
Well, it might
Can
be
you hear
close.
me?
Yeah, I can hear you. I can
All
hear
right,
you.
so basically what you're supposed to do is supposed to take the receive and then, it's supposed to take the transmit, and once you receive, it's supposed to come in, and then it goes through the steps in reverse. It would go through the down convert, the demodulation, and the demultiplex, and then it would come to the sound.
Well, you're close. Can Johnson tell us the 3 steps in order? He's missed a step. Do you know what step it was?
The LNA?
Yeah. Amplification is first, which is good. Then you got down conversion, so you're going to take the RF to IF. And then the last step is, demodulation. And you're taking that IF to the aggregate. And then when you send it all over to the multiplexer, that's where the demultiplexing comes into play. So Johnson, what is the definition of frequency response? You can type it in on your chat there. I can see it. The advantages of a dual monitor. Johnson, are you there? Just a simple thumbs up will help. Johnson.
Are you able to hear me now?
Yes, I can hear you.
Sorry,
Good.
my computer's messing up. I'm not exactly sure. I went to the bathroom for that part.
All right, let's get one thing straight here. If you gotta go to the restroom, can you please say, hey, down in the chat, because I can see it, just let me know that you've got to go to the restroom. All right? We'll probably take a 5-minute break just because. All right? So the whole idea here is to make sure everybody's on the same page and you don't miss this information. So please, Aaron Johnson, next time that happens, just let me know, because I don't know if you've got up and walked over to the bathroom or you went down to, let's just say, the hallway there to get you something to eat. You know, that's really not how we work things here. You don't get up and get out of the classroom to go to the bathroom unless you say, hey, I got to go. You know, because there's some things in here that are extremely important. And if you don't hear it, when you got to go over it and try to regurgitate the information, it may not become clear. And it's very possible it could be on the test. So just letting you know, please, as a nicety, to inform me, hey, I got to go, please, put it in the chat. We'll stop, especially if it's important, and we'll go from there. All right, Wagner, can you tell us what frequency response would be, the definition?
It's just the measure of a system's response to a frequency.
Okay.
So,
whether it's produced or reproduced, how well it's able to do that. Good. All right. James Richardson Smith, you guys got any questions?
No, sir.
No, sir.
Okay. All right. Does anybody have to take a break?
I go for a break, sir.
All right. So let's do this. Remember now, I have the primary clock. I have 9:43 a.m. That means be back at 9:48, please. And we'll go from there. Any questions?
No, sir.
All right, let's go on a 5-minute break. We'll be right back. Oh, shit, my back. Vanilla? Okay. I have my boss online. Everybody back?
Yes, sir. Yes, sir.
Okay.
Yes,
Abul, you there?
Yes, sir. Yes, sir.
Okay. Bakken,
Yes, sir.
Garcia, and Johnson? Okay.
Yes.
All right. And Wagner? Wagner, you there? May not be back yet. Wagner?
Yes, sir.
All right. We got everybody. All right. So we looked at the summary, or we're looking at summary basic radio picture, fundamental radio parameters, radio performance assessment, and ancillary functions. Let's look at the next one, which is identify basic facts and principles, capabilities and limitations of modems. Just remember, again, you can only miss 12 on the test. It's a 40-question test to get at least a 70 to go on to the next block. Prefer that you get more. And again, SI is available. We will be starting tomorrow with it. Like having an eyelash hit your eye and you can't read. Let's look at our AFSC application. You guys have been playing with modems since you guys got computers. So you do have the capability, you just probably weren't aware of it. Let's take a look at each one of these. We got general modem principles, types of modulation, forward error correction, interleaving, traditional modems, and IP-based modems. Modems, what the heck are they? Well, the idea here is we're going to take a digital signal, convert it into an analog carrier, and send it to the distant end. Depends on that type of carrier, what we end up doing. The distant end is going to demodulate it, put it back into an aggregate, and send it to, fill in the blank. You can have voice on there. We went through PCM to show you how analog, where you go from analog to digital, and then digital to analog is the reverse of the process. You guys have probably seen this word in Block 6 and have come across it many times in your wonderful world of the computer technology. What is baud? Well, it's a speed known as a symbol. Interesting. It is also determined by the modulation type as to how many symbols you can have. You got bit rate versus baud rate. Bit being the ones and zeros in a word. An 8-bit word can transfer as maybe one baud. You just don't know. And you can have as many as 10 bits per symbol today. I'm probably certain now that there's probably more since they're working on a 10K TV. Modulation types. We have frequency, amplitude, and phase. These are the three basic ones that you've seen out there. Let's take a look and go through each one of them. So first one is frequency shift keying. This one is using ones and zeros, of course the logics, and one frequency is a 1 and a 0 is a different frequency, and we classify this as 1 bit per symbol. FSK is 1 bit per symbol. Let's look at the waveform with the data. You can see that anytime we have a logic and it continues, nothing happens. It does not change. The moment that it changes from a logic 1 to 0 or a 0 to 1, the frequency changes. You can see that anytime we have a logic of 1, it's a higher frequency. Anytime we have a logic of 0, they're lower frequencies. Pretty self-explanatory. Next up, we have amplitude. Now, in your study guide workbook, they always talk about the voltage. Voltage, you increase the voltage on an analog signal, you increase the amplitude. You decrease the voltage on a waveform, you're going to have a decrease in amplitude. Works the same way. It is also 1 bit per symbol. ASK, 1 bit per symbol. Here is the diagram we show. You can see that we have a 1, we have a large amplitude or a large voltage. For any zeros that you see, it's a lower amplitude or a lower voltage. That's ASK. Next up, we have something called phase shift keying, PSK. There are two different types that we go through. One's binary, the other one's quadrature. Let's take a look at the binary. This one is 1 bit per symbol. Now, the only time that it is really truly going to shift is when we change logics. And there's going to be a 180-degree phase shift with it. We're going to show you what it means by 180 degrees phase shift. When you look at the waveform, this is binary phase shift keying. Anytime that we change the logics, that's where the phase shift occurs. Everybody see that on this particular waveform.
Yes,
Okay?
sir.
All right, so the next one is something called quadrature. This one has 2 bits per symbol. Now, why is that? Well, 1 bit was either a logic 1 or a logic 0. It's either or. With quadrature, get this, doing the research on it, there's 2 carriers that's on it that can go between a 0 and a 1. Is considered pretty doggone good when you compare it to the first 3 that we looked at. The difference is now you have a 0, 0 with those, or a 1, 0, or a 0, 1, or a 1, 1. That's the reason why it's called 2 bits per symbol. You can start to see how this is all going into play. Now, QAM is a little bit more. This one, and I pulled this out of trying to make heads or tails out of the calculus that they were showing me, but you can get 3 or 4, you can get all the way up to 10, but it just goes to show you, and this is what I got from it. It has a 4 quadrant, you have X and Y axis, and you have carriers on each one of those X and Y axes, and I'm showing you here that you could have 2 bits. In this case, it has 8 bits per symbol on this one particular one that I could decipher. Again, this is extremely difficult to go to YouTube or any of the other websites in trying to figure this out. So let's keep it simple. Anything that says QAM means that you're going to be at least 3, if not more, bits per symbol. So it's showing you the technology that's out there that you're probably going to encounter as technology grows within the Air Force. Now, we deal with the first three, keep it simple, 1 bit per symbol. When you get to the quadrature, you're dealing with the quadrature phase shifting, you're dealing with 2. Okay, that's where we start seeing anything. So the easiest way to remember it is anything with the simple names in it, amplitude, frequency, binary, those 3 are 1 bit per symbol. Anything with a Q in it has more than 1 bit per symbol. Now, why is this all, have anything to do with anything? We're getting there. We have something called forward error correction. Now, this is basically what I classify as the wheel of fortune of reconstruction for bits of information. It's the easiest way I could think of. What does it mean? Well, I'm going to send this data from one computer to the distant end. Well, the last thing I want to do is keep resending everything because it gets to be old and just downright frustrating at times. So the idea here is I'm going to start sending correction bits to the distant end. If you were to look up forward error correction, you would find something called Hamming code. Again, that's one of those things where you can understand the professor's name, and for the first couple minutes, you're just dazzled with how they're able to work this forward error correction or Hamming code, and how they're able to put it back together using mathematical equations. Pretty ingenious. What we are going to do is keep it simple by looking at the forward error correction rates. You'll see that the first number says 1/2 or a half, whatever you want to call it. And the easiest way to picture this is you're going to send 2 bits of signal down to the distant end. The network was dropping out for the last 3 minutes. I didn't catch what was said. Oh no. Okay. Here's what I'm going to suggest. Thank you for letting me know. I do record these, and I'll try to get this up for you as soon as possible. Do you know where you stopped at, Airman Botkin? I can catch you up. No. Where did we leave? Where did you drop out at? Or do you want to watch the video later? Which one do you want to do?
I'll watch the video.
Okay, we can do that. All right. I have your word on it, right?
Yes, sir.
Okay, because all you can do is fast forward to the piece you missed. That would be the easiest way to do it. All right, so we left off with the half. Again, I said that it's going to send 2 bits of information. The first bit is going to be the intelligence. The other bit is going to be the error correction. When you look at 3/4, it's going to send 4 bits of information. 3 of it's going to be the intelligence. The 4th bit is going to be the correction. All right? And so forth and so on. Why is it that we go through the types of modulation and forward error correction? Well, you need these two along with data rate to figure out overall baud rate or symbol rate. So you have data rate, modulation type, and this is where that bits per symbol comes into play. I'm not sure if Mr. Miller kept that in the study guide workbook, but there is a mathematical equation to figure out overall baud rate by using data rate, modulation type, and forward error correction factor. So if you want to, you can try it out. Again, those 3 are really important when it comes to figuring out your overall system baud rate or symbol rate. Here is a picture that gives you an idea of how everything is being put together. You can see that we have the data rate, what's the multiplexer coming in with, then you know that you're going to be sending out forward error correction, and then the modulation type. Next up, we have something which is called interleaving. The way they classify that, it mixes data using time division to correct for errors or recover lost bits. The idea here is when we only lose a bit from a block, then the whole block of data. Now, why is all this important? Well, if you're still on wires, you're probably going to get noise. And it is very possible that you're going to get it. Or if you even use HF where there's noise on our signals. It's inherent to HF. However, HF is getting better because they went to this QAM, and I'm hearing pretty good results when they use QAM as opposed to the others. Next up, we look at traditional modem types. We have telephone modem, you have a satellite modem. Telephone is back in the day with a rotary dial, then it went to the frequency shift keying dial, you know, things like that. Everybody has talked about the 56K dial-up. YouTube actually has a video on what it sounds like, and it brings back old haunting memories. We also have a satellite modem. Now, you guys have already looked at a satellite modem, or at least I thought I told you about it. Remember when you walked into room 116 and told you to look to the left? Nobody?
Yes, sir.
Okay, and what did you see?
Satellite modem.
Yeah, and what's it called?
I do not remember.
Well, you got the I part right. iDirect. Okay. Well, let me show you here what the iDirect looks like. See if you can remember. I'm going to flip to scene 2. Look at the bottom left of that picture. Was that what you saw when you walked in and looked off to the left?
Yes, sir.
That's your iDirect modem.
It's very loud, too.
Yeah, when they got that thing turned on, not only does the 3 cases, you know, it's loud to begin with, but when they turn that one on, it increases. It's the reason why I encourage you, if you ever go back in that room, to wear hearing protection if you feel the need to. That does not mean that you can wear your earbuds, okay? It means that you can wear hearing protection, okay? Next up, we have something called a fiber optic modem. Now, these are very high rates. Again, this is not susceptible to any of the RF that's out there or electromagnetic interference. Why? Because when you look at a fiber optic modem, it's on light. Now, you guys remember at the first part of this, I told you you can see RF, and light is considered RF if you look at the frequency spectrum, international frequency spectrum, and it's in the terahertz. Different colors are different terahertz. So this particular, or the fiber optic modems work in 5 stages. Stage 1 is the modulator, stage 2 is a transmitter, stage 3 is a receiver, stage 4 is a filter, and stage 5 is a demodulator. This is the steps it works in. Don't get them confused. And then, of course, we have the IP-based modems. These modems are always on, i.e., for example, when I come in here in the morning, I turn on 2 different computers. I've got my AFNet computer, which ties to a VPN, and I can get most of my work accomplished through that way. And I also have a big rig that I like to call, and I turn that on. When it goes through its checks, it automatically hits the modem, except for the AFNet, you got to tie it to the VPN. It still sees the modem, it's tied to it, but it uses the VPN to go to, in my case, it goes to Lackland. So these are always on. You know, when you guys fire up your laptops and you connect to Boingo, it's searching for that connection and automatically gets turned on once it finds it. Again, Boingo's slow. I understand. Next up, we talk about the iDirect modem a little bit. And this is just to give you an overview. If you were to look at the actual book It's really difficult to pull these things out because normally these are on the first couple pages, but this one, last time I looked, like 2 years ago, it was in the back. It multiplexes 30 terminals into just 4 carriers. We'll look at those 4 carriers in the meantime. FDMA will need 60 for the same. That's just giving you a idea of the comparison between FDMA and TDMA. High performance, secure, portable system that transfers voice, video, data across satellite. No. Yes. Here are the 4 bands that it goes through. You got the C band, the X band, the KU, and the KA band. All right, so what does that mean to you? Well, if you looked it up on the frequency spectrum, say you typed it in Google, you will find out that the C band and the X band, the KA and the KU band all have places in that spectrum. I think it's starting about 2.3, maybe 2.5 for C band, all the way up to the KA top end band. You're looking at about 40 gig. So 2.5 to 40 gig. Now, if you'll notice, it says CX, KU, and KA band. Wait a minute, where's the K band? Well, we don't use the K band for this type of modem. The easiest way to look at KU and KA is KU is the frequency range is under the K band, and KA band is frequency range above the K band. So if you were to go out tonight and look on Google, you'd be able to see that. And it lists the frequency ranges of each one of those. So it just gives you an idea. Now, the easiest way to remember this is Sergeant Young told me probably about several months ago. He says, the way I can get these students to memorize this stuff if they need to is the CX and the KUKA band. I'm like, okay, whatever works for you. If that's the way you want to remember it, go for it. I thought that was kind of ingenious because my son listens to K-pop band and I like to kid him about it every now and then. Anybody in here like K-pop?
A little bit.
Yes, sir.
I like, it's funny at times to listen. Ooh, Dad. Anyway.
I like J-pop more.
Huh? Not heard that one. I'll have to go and look that one up. So, learning stuff new today from you, eh? All right. So as you can see, that it pretty much does everything that a modem is supposed to do. This should be interesting. But it just gives you an idea of what an iDirect is, capable of doing. So again, when you look at the iDirect, you're looking at the 30 terminals and comparing it to the 60. It's possible that it could use, but the frequencies that it's using are the CX, KU, and the KA bands. All right, so we've looked at general modem principles, type of modulation for their correction, interleaving, traditional modems, and IP-based modems. Airman James, question for you.
Yes, sir.
What are the 3 types of 1 bit per symbol for types of modulation?
1 bit per symbol?
Mm-hmm. Just name one.
It's not. That's not frequency shift, right?
I don't know, is it? Airman Richards, is he
Can't
right?
remember.
Yeah, frequency shift or amplitude shift.
Okay, and Airman Smith, what would be the third one with 1 bit per symbol?
BPSK.
Yep, binary phase shift king. Abul, name me one that has more than 1 bit per symbol. We listed 2.
It is the quadrature phase shift king.
Excellent, excellent. All right, what 3 things do I need in order to find out what my symbol or baud rate is, Airman Alvarez?
Could you repeat the question, sir?
Sure can. In order for me to figure out the baud rate or symbol rate, there were 3 things we mentioned that is needed for that. What are they?
Oh, it's data rate, the FEC factor,
Okay.
and I can't remember the third one.
Okay. Can't remember the third one. Anybody? Anybody? All right, let me go back to it.
Is it modulation?
Modulation.
Modulation type. So data rate, forward error correction, modulation type. All right. Any other questions on this particular one? No? All right, so let's look at 4 alpha. Let me get this. For some reason, the last couple of slideshows have a tendency to off-center themselves, and I don't have any idea why. They're all the same 108%, and I don't know what I'm doing wrong, but the last like 4 alpha, Bravo, and Charlie all have different areas on my OBS here. So let's look at identify basic facts and principles, capabilities and limitations of line of sight radios. As you well know, you guys have played with the frequency spectrum before. We're just going to help you narrow it down to what's called line of sight. The overview looks like at line of sight principles, repeaters, and limitations of repeaters. Before I go any further, let me grab some C's and D's here. You guys should have electronic C's and D's. And let me look real quick. Wrong way. Gosh darn it. Bring up your, here we go. This is the handout 3D 133-7-5, and what it does is it has the electronic version of what we're getting ready to go over. So if you can bring that up, that would probably help. If you don't have the capabilities of doing it, please look at it later. Get back to my original one here. Line of sight principles, repeaters, limitations of repeaters. This is a definition. It goes hand in hand with the one that you learned in Block 4, except for we are looking at more of what's called a unidirectional antenna. Not a omni, not a bi-directional antenna. We're looking at a unidirectional antenna. You can get away with some obstacles in the way when we are looking at, let's say, a vertically polarized omnidirectional antenna. You can probably get away with a bidirectional antenna called diffraction and multipathing, which is a bad thing when it comes to looking at line of sight. But when you deal with what's called a Yagi style antenna, anything that gets in the way of it, you're probably going to have no communication. So that's what we are looking at now. Let's look at line of sight principles. Okay, and this is where that, bring that up again. This is a better, let me move this where you guys can see it. This is a page 1 of your C's and D's. This is a better drawing, but you can see where we have the true horizon compared to optical horizon. Its optical horizon is 18% farther than true horizon. When you compare it to radio horizon from true horizon, it's 33%. Okay, so this is in your C's and D's, page 1. Let's go back to the slideshow. You notice that there's something missing here. That's because of the picture. We're trying to blow it up for you to give you an idea of where those figures came from. So radio horizon extends 15% farther than optical and 33 more than true. Next up, we have line of sight. Typically, what's that word? Typically operates on the following: 20 to 50 miles is the range. Frequency is 3 to 50 gigahertz and power is 1 to 5 watts. On the TISR, it's only 316 milliwatts. Yeah, pretty interesting. SATCOM's a lot more, okay? So, again, that's nothing more than pointing it directly up in the air. Well, I shouldn't say directly, but you're pointing it at an object up in space, but you got to punch through a whole bunch of atmosphere to get to it. What are some practical applications for line-of-sight radios? Well, in our case, cable replacement. How many wants to dig like 3 miles, hand dig it, just to put cables in place? Not me.
That sounds enjoyable.
No. Backhoe maybe, and even then it would be rough. What happens if you're in a rocky terrain? Do you want to try to blow rocks up so you can lay cable under the ground? I don't think so.
I mean, that would be the fun way to do it.
Yeah, blowing stuff up. We know where you trend to there, Wagner. Blow stuff up. All right, but it's just on a practical application. The idea here is I don't want to lay a whole bunch of cable. So with terrain, again, yeah, Sergeant Sackett says, blow stuff up. Yeah, I love that. Anyway, your terrain too also plays in a part. Let's just say that you got to get over top of a mountaintop. Okay. Well, yeah, you could do it, but what you need is, and that's where the extension of the radio horizon comes from, because you can't get over the mountaintop. That's where a repeater would come into play. Now, in Block 5, you guys talked about repeaters, didn't you?
Yeah, sir.
Okay, so that's extending the radio horizon, so to speak. In our case, we're going to use a Yagi antenna to get to the top of the hill or mountain, and then the other part's going to relay it back down to the other side of the hill. So terrain, distance, how far is my radio going to go too? Well, repeaters are going to extend that distance too. Let's say that my equipment can only go 20 miles out and I need to go 40 miles. Well, now I need a repeater. So these are practical applications for line-of-sight radios in what they can be used for and when a repeater comes into play. Yeah, I would be that person that want to get that first fuse lit up, right? Not your typical 4th of July fireworks blowing up rocks. All right, so repeaters are transmitter and receivers together. Okay, there's 2 things it must do. First of all, is frequency translation. Next one is amplification. Those 2 are 2 functions that are needed to do that. Frequency translation, I like to use frequency conversion, so those 2 are interchangeable. Next is amplification. Again, when you pull up your C's and D's, page 2 is a place where you can find 2 of the repeaters that we go through. 2. That wasn't cool. Fat fingered that one. So we have 4 types of repeaters, even though we showed 2 on the C's and D's. There's 4 types that we go through. We have an RF repeater, an IF repeater, and a baseband repeater. and an audio repeater. Let's look at each one of them. So again, this one is on our C's and D's. You can see it. It shows you everything you need to know. There are two things that we need or must have, and it does it. First one is frequency translation or conversion. What does that mean? I'm going to change the receive frequency to a different frequency in transmit so they don't interfere. So let's take a look at it. That's the first step. So we get 440 coming in on our receive. We go through the mixer, and instead of 440 or 4400, we get 4660. So there is your frequency translation or conversion, and it's not going to interfere with that receive frequency and retransmit it out as a different frequency. What's the second part of this that must happen? Anybody? Okay, we did frequency conversion. What's the second step that we got to have in there? James, you know?
I'm looking at the chart right now, sir.
Okay. Bakken, any idea?
I do not, sir.
Okay, well, at least you're honest. Abul?
No idea as well, sir.
Okay, well, let's go back 2 slides. What 2 features must the repeaters do? Frequency translation. What's the second one?
Amplify.
There you go. Amplify. So where do we get it out of here? Well, there you go. Here's your LNA and HPA. Those are your amplifications. So it did its 2 things that it needs, which is frequency translation, converting it from one frequency to another, and then the other one is amplification, which it did. It took the receive signal, boosted it up. Now I can mix it with the local oscillator, and then when I get ready to resend it out, I amplify it to the point where I know it's going to get to the distant end. Voila. There you go. So the problem with the RF repeater is it doesn't break it down where it cleans the noise out of it, so it ends up with the most distortion. Okay? Distortion is not good. Next up, we have an IF repeater. This one breaks the signal down to the IF performance. In other words, we're going from RF to IF from a basic radio standpoint. It's still doing the frequency translation or conversion, converting it from one frequency to another, but it's also doing the amplification. The nice thing is when it starts breaking it down, it can clean the noise out of it better. And you're going to see throughout every radio, the more you break it down, the more filters it has on it, and so forth and so on, so that we don't have a whole lot of noise. So in this case, we're going to amplify a receive signal because it's always weak. We're going to down convert it using a local oscillator to 70 megahertz. Typical IF. We're going to use an IF amplifier because anytime that you manipulate the signal, you got to amplify it. We're going to take that 70 megahertz. Now we're going to up convert it. Kind of reminds you of the basic radios, doesn't it? And then we're going to up convert it to the frequency translated different frequency than it was received, get amplified again, and then send it out to the distant end. So it met the 2 requirements of frequency translation and amplification. The difference is we broke it down to the IF side so we can clean some of the noise out of it. So it's a lot better than our RF repeater. We also have something called a baseband repeater. This one is going to break it down to the aggregate signal. So the basic radio comes into play really well. So you're going from, to receive the signal, you're going to amplify it, down convert it to IF, from RF to IF, and then you're going to demodulate it to the baseband signal, which is the aggregate. You have at that point the capability of taking that aggregate and changing it. You may want to add or take away, because you could say that that repeater site is a hub, so to speak. So you can add to or take away. Again, this is a little bit better than the IF one. Why? It's breaking it all the way down to the aggregate. Now, the TISR can do this. And we've done it in the past when we had all the equipment available to us. Normally it was done on nights because during days you couldn't get all the equipment. Again, it's a baseband repeater. Next up is the best repeater that's out there. And when they say audio, they are breaking it down into the user's information. Again, it does have the capability of, dropping off information and reinserting information. But the problem with the audio repeater, because it's so good, it's expensive. And money talks when you need stuff like that. So what are some limitations of repeaters? Well, distance is one, because you can only go so far with the, depending on how many repeaters you need. Again, it all has to do with equipment capability, what the terrain is like, and the last one, which is the most important, was what I'm calling for, is the needs of the communication network. Normally, this is where everybody stops and goes, well, I need the distance, I need the equipment, I need the terrain. How about your money? Oh, we don't have any. Well, if you really needed that equipment, you would be getting that equipment. So that's the key part there. Normally the needs of the equipment, if there is a very significant need, the money's going to come. So that's how you can tell whether it's needed or wanted. And being in the LMR, I saw a lot of wants, but there was very few that were needs. When I say that, LMR managers normally take care of all the frequencies that are on the base, as well as cell phones and a couple other things. And we have an insight of when we see repeaters like this, because I worked heavily with repeaters for the Utah Test and Training Range. And the needs of the network, there were a bunch out there that needed that comm to get to the dis and in. And it was, the money was there at that point, and we got that network up for them. Also, when we do this, as far as the limitations of the repeaters, we need to know the noise factor. Obviously, for your RF is very few links. In our case, it's 8 consecutive in a row. But TDM, which is breaking it down into the aggregate, you got 15. So you can see the difference between the two. So we've looked at line of sight principles, repeaters, and limitations of repeaters. Any questions?
No, sir.
Okay, this was a pretty simple one. So let me see if we have got one more before we go to lunch. This should be pretty quick. This is identify basic facts about tropo theory. Again, got to readjust. Okay. I think I've stated enough about the test. Tropo. Okay, that's the big thing. Tropo. That's what we're going to be using with some of our equipment that's out there. The two devices that you saw on the last slide, I saw a lot of those on Fort Gordon when I went up there to train on the TSC 179 and the TISR, as well as the FCC 100 multiplexer. Those were tropo. electronics. So we look at tropo communications, antenna terms, and tropospheric antennas. Take a look at these. Troposcatter. This is where we're going to use the tropo to refract signals back down to Earth. Now there's an area, normally it's that convergent zone between the tropo and the stratosphere is where the most refraction happens. Most of your signal is going to keep going right out to the atmosphere, into outer space. Never to be seen or heard from again unless there's aliens and then they know what we're doing. Power, anywhere between 300 to 50,000 watts, just to punch a signal through 600 miles. Now, if you look at the range, okay, it says 595. Well, if you look up on credible websites, it's anywhere between 580 to 610. Why they chose 595, I think they were looking at in the middle. So it just gives you an idea. Freq range is 350 megahertz all the way up to 8 gig. And if you're in the tactical environment, like you saw in the last slideshow, it's 150 miles tactical. Normally, you're not going to transmit 50,000 watts if you're in a tactical environment. It's more like 300. Why? Because you don't want to become a target. Just let the equipment be your target. That little area that refracts back down to Earth, we call scatter volume or common volume. Those are the two words that are interchangeable between the two. Again, it is reliant on the receiving antenna because you're getting so little of that information. Troposcatter has what we call a diversity system. Now I can go into detail with this, but I'm not, because the tissers should be able to give you an idea as to what what the relationship is as far as polarization, angle, space, and frequency. Every one of those is used with that Jerk 239 that's right above my head. Pretty cool in my opinion. And we're going to reference this on a couple occasions when we go through the Jerk 239. We have common volume or scatter volume, and of course it's that little area that gets refracted back down to Earth. We have a couple antenna terms, some of you seen. Reciprocity, transmit and receive well on the same antenna. Got directivity and gain. Higher directivity, higher the gain. Lower directivity, lower the gain. It's pretty obvious. If you got an omnidirectional vertical whip antenna, you're going to have pretty low gain. If you got a Yagi antenna, which focuses everything on the front end, you're going to have some really high gain from it. Next up, we look at frequency. So, has everything to do with that wavelength. Higher the frequency, smaller the antenna. Lower the frequency, the larger the antenna. Not to be confused with the dish. The dish is what can give you gain. The antenna is actually located at the back end of the waveguide on the equipment. When you're dealing with gigahertz, your antenna's about the size of about a 1/4 inch. Yeah, it's pretty small. So when you look at the dish, it is not, just because you have a large dish does not mean you have a large antenna. It just means that your dish is collecting a lot of information. In other words, it has a lot of gain to it. Again, there's a couple different types of antennas out there that we look at. One's called a horn, the other one's called a parabolic. And the idea here is to get all that energy to focus in on the antenna. The horn, you've seen this back in Block 4. It is the simplest type. It directs energy in the desired location. In other words, it's focusing in on that very small antenna. And it does have some impedance matching characteristics. We have a parabolic antenna, and that's the dish. Again, that size and gain are directly proportional. In other words, the larger the size of your dish, the better the gain. It also means that you can focus it more. excuse me, we have two different types of feeds. One's front feed, one's a rear feed. So parabolic normally has either a front or an offset. Excuse me. And they're either, center or offset with it. And the rear feed has two different types called a Cassegrainian and the Cutler. Now the Cutler is what the Jerk 239 uses. We'll get that in just a minute. This is what a parabolic looks like. This is a center-fed antenna as opposed to an offset. The offset you've seen when you go by Jones Hall and you see that gated in area where all the satellite dishes are. You can identify them. Excuse me. You have a Cassegrainian. This is a rear fed. Again, the Cutler is a rear fed. You can see where the feed horn is on the dish in the back side of it. Well, the antenna is right after that feed horn if you're receiving, or the first thing it's going to transmit out of the feed horn. Now this sub-reflector is concave, okay, just like the dish is. The idea is we're going to do what we call a double bounce off of it when we're transmitting. Again, the feed horn, if I'm looking at the feed horn on the middle diagram here, that antenna is in the back of the feed horn or the left-hand side of it. When it transmits, it goes through the feed horn, bounces off that parabolic subreflector, then bounces onto the dish, and then gets reflected, looks like, out through the front end. In other words, you're focusing that signal. Next up, we have a Cutler. This is, again, another what they call a double shot or a double bounce. This one has two metal reflectors, and they look like this on the waveguide, and underneath those reflectors, there's a rectangle hole in there on both sides. It is considered the narrowest beam width and the highest gain. Again, if you get into the Tisser lab and you can remember it, take that Cutler waveguide, flip it upside down, and look down into those metal reflectors, and you will see that rectangle hole. That's its entry and exit point for transmit and receive. And it bounces off the dish and goes out forward for transmit and receives it the same way. So we've looked at tropo communications, antenna terms, tropospheric antennas. Any questions on this massive bit of information?
No, sir.
Okay.
Yes, sir.
So here's what we're going to do.